Hello student. Today I am going to discuss very important topic for your upcoming JEE and NEET exam. As far as chemistry is concerned, the number of revisions always directly proportional to your marks into the JEE and NEET. So that's why if you increase your number of revisions, your marks also will increase in JEE and NEET. For this 2025 JEE and NEET, you have to follow few tricks for the revision of chemistry. As far as chemistry is concerned, it is very scoring subject if you are able to do the proper revisions. And for that revision plan, I am giving you the tricks how you will go for the revisions of chemistry. Let us start with a very important chapter of chemistry, how you will go for the revisions. That chapter is nothing but a equilibrium. So if you look at this equilibrium chapter, equilibrium is composed by, there are two parts. One is chemical equilibrium and one is ionic equilibrium. In chemical equilibrium part, you have to cover up first what is the definition of equilibrium, chemical equilibrium, definitions of chemical equilibrium. That means you need to know, that means at equilibrium, the rate of forward reactions will be equals to the rate of backward reaction, as well as it is dynamic in nature, as well as at equilibrium, the concentrations of reactant as well as product may or may not be equal, but the rate of forward reaction, that means reactant to product conversion as well as rate of backward reaction, product to reactant conversion, that rate should be equal. In graphical representation also, several times that part also came into the questions, graphical representations of that one. So now next, equilibrium constant. Equilibrium constant is nothing but that your forward direction rate constant by backward direction rate constant. This is a rate constant. In chemical kinetics, there is a detailed discussion is there in rate constant in Arrhenius equation. This is also rate constant, but F means forward direction, B means backward direction. Then equilibrium constant equals to K by KB, and that expressions and equilibrium constant can be expressed in terms of a concentration, in terms of a partial pressure of reactant and product, and in terms of a Kx, which is a mole fraction. That you need to know. And always equilibrium constant expression, product by reactant raised to the power of their stoichiometric coefficient. In terms of a concentration, active mass or molar concentration of product raised to the power of their stoichiometric coefficient by active mass or molar concentration of reactant raised to the power of their stoichiometric coefficient. Whereas Kp, partial pressure of the product raised to the power of their stoichiometric coefficient by partial pressure of reactant raised to the power of their stoichiometric coefficient. Mole fraction, same way, mole fractions of the product raised to the power of their stoichiometric coefficient by mole fraction of reactant raised to the power of their stoichiometric coefficient. That way we can express that equilibrium constant. Then among them interrelations and specific problem based on based on Kp, Kc and interrelations. After that, very important topic, what are the parameters is influencing the equilibrium constant? Generally Kp, Kc will only depend on temperatures, no other parameters, but mole fractions in Kx it will depend on pressures, but Kp, Kc only will be changed whenever temperature is changing. And what is the effect of other parameter of reactions on the equilibrium conditions? That means if I increase the temperature for exothermic reaction, for endothermic reactions, which directions reaction will proceed? Then if I add the inert gas, then in constant pressure, in constant volume, what will be the effect on equilibrium constant? If I increase the reactant concentration, what will be the effect on equilibrium constant? If I increase the product, then what is the effect on equilibrium constant? That part. And then we need to go after Kp, Kc, all those things. Then we need to go degree of dissociation. DOD you need to know. DOD means always it is a fraction. Fraction means it will be out of 1. Out of 1. Out of 1. Suppose if they are telling DOD is alpha, DOD can be expressed by anything. But meaning wise, out of total number of moles, how many mole is dissociating? That is nothing but out of 1. So then always you have to remember DOD is nothing but a fraction out of 1. And POD is nothing but a percentage, means out of 100. Like that you remember, you will never make a mistakes. POD means out of 100. So then immediately you can write down DOD into 100. DOD into 100 equals to your POD. If POD giving, then divided by 100 you will get DOD. If DOD given multiplied by 100 you will get a POD. POD by 100 DOD. Everything you can interconvert it, whatever way they are giving. POD means percentage of dissociation. DOD means degree of dissociation. So now based on that related problem, that means suppose if you have a like this reactions, N2O4 is converting to 2NO2. Whenever they are not mentioning anything, always you take initial number of moles is a 1. That means when time t equals to 0, it was there 1, it was there 0. Then my DOD is if I alpha, so then my time t equals to t equilibrium reach, how much dissociate? Out of 1 mole, how much will be dissociate? So I told DOD means out of 1. So out of 1 dissociate how much? 1 into alpha. That means 1 minus alpha. Here 1 mole used to form 2 moles of NO2. Reaction will occur always as per stoichiometry. Here situation will be how much? 2 alpha. Then you need to find out that if I am telling if total pressure at equilibrium, I am telling is P, then Kp expression you have to derive. That process is there. Everybody knows. If you don't know, you follow my videos, there detailed discussion is there. Kp will be equals to 4 alpha square P by 1 minus alpha square. So like that relations for all types of gaseous reactions, like PCl5 dissociate into PCl3 plus chlorine, N2 plus 3H2 forming 2 ammonia. Like that all types of gaseous reaction, H2 plus I2 equals to 2HI, you can derive like this expression which will help different types of problem and that related problem. And again you need to know that 1 plus N minus 1 into alpha, alpha is the degree of dissociation, capital D by small d. This is capital D is a theoretical vapor density, theoretical Vd, small d is a equilibrium vapor density, equilibrium Vd, and N is a number of moles of gaseous product form from 1 mole of gaseous substance, This relations you have to remember. Based on that they used to give the problems. And basically these are the important point as far as chemical equilibrium is problem, and it's a numerical based problem. You need to solve a lot of problem based on these. Yes or no? Then let us focus for ionic equilibrium. So in ionic equilibrium, if you look at in ionic equilibrium, what we need to know? In ionic equilibrium part, if you look at ionic equilibrium, first we need to know basic idea. Equilibrium is existing between molecule and ion, but chemical equilibrium, reactant also molecule, product also molecule, in between them equilibrium present. First you will go for Ostwald dilutions law. Ostwald dilutions law for weak electrolyte. Dilutions law for weak electrolyte. I hope you know what is weak electrolyte. Like acid, base and salt is a weak electrolyte, and that means weak acid, weak base. For that, what will be the scenario? Like Acetic acid, I hope everybody knows these things. Weak acid we used to write down like this, Wa. Weak acid, dissociate like this, acetidine and H plus. And then immediately you know that at equilibrium what will be my situation if degree of dissociation alpha and initial concentration is this was C, then at equilibrium C minus C alpha, C alpha, C alpha, and from there we used to derive that equation, dissociation constant K will be equals to active mass or molar concentrations of the product raised to the power of their stoichiometric coefficient by active mass or molar concentrations of the reactant raised to the power of their stoichiometric coefficient, and we used to put C alpha into C alpha, C into 1 minus alpha, and we used to take approximation 1 minus alpha will be equals to 1 whenever alpha should lesser equals to 0.1 or 10%. 10% means 10 by 100, which is lesser equals to 0.1. If it is not there, we can't take 1 minus alpha equals to 1. This approximation is taken to avoid the quadratic solving the equation. To avoid the quadratic equations, we used to take the approximations over here. If it is not matching that criteria, we can't take that approximations. 1 minus alpha almost equals to 1. So then you have to solve the quadratic equations. K value will be provided and you have to get the exact alpha values. And then here we are taking that approximation. That's why we can get these and these cancel out, and we used to get C alpha square equals to K. That's why alpha equals to under root of K by C. We used to get like this, and you need to have a very good clarity over here, like that whenever my concentrations decreases, that means when I am going for dilutions, alpha will be increases, that means degree of dissociation will be more, as well as my number of moles of H plus will be more. Number of moles of H plus will be more. But you look at how the concentration is decreasing. If the number of moles of H plus is increasing, because concentration equals to molarity, which is N by V. If the number of moles increment is there 1 unit, volume increment will be there 2 unit, overall concentration is decreasing. This is the idea. That way, that's why if concentration at degree of dissociation are inversely proportional. Another point is very important. When C tends to 0, that means when we are going for infinite dilutions, then alpha cannot be infinity, because degree of dissociation maximum value is possible how much? 1 out of 4 molecule, 4 dissociate. Then or out of 4 mole dissociate. That's why 4 by 4 degree of dissociation maximum can be 1, percentage of dissociation maximum can be 100. So that's why you don't think mathematically, you have to think physically. Out of all are dissociate. That's why it will be maximum will be nothing but a 1. So that is the idea you need to know over here. That means weak electrolyte at infinite dilution can behave as a strong electrolyte. That way also you can do for the bases, weak bases you can do, and you can apply all those things, that related problem you can go it far with this. Next, what you can do? For you can go with a pH calculations. I hope you know, minus log of H plus concentration base log 10 base. These things you need to remember. Always H plus concentration you will take in this form, X into 10 power of minus Y. Molarity of H plus. Directly you can write down pH will be equals to Y minus log X. And log 2 value, log 3 value, log 2 is 0.3, log 3 value is around 0.48, log 5 value is 0.69, log 7 is 0.84, and log 1 is 0, log 10 is 1. So like that basic value you have to remember. And now POH also same thing. POH will be equals to minus log of OH minus concentration base 10. And then always you have to remember pH plus POH will be equals to 14. Very important. Based on that problem will be there. Then pK plus pKb. pK plus pKb also will be equals to 14. Ka is nothing but a dissociation constant of acid. Kb is a dissociation constant of base. Especially for weak base we used to utilize that one. And always you have to remember K into Kb will be equals to Kw. Kw is a ionic product of water. Kw will be equals to always H plus concentration into H minus concentration for water. And at 25 degrees centigrade, for water, this concentration will be 10 power of 7 moles per liter, and as well as OH minus concentration 10 power of minus 7 moles per liter. We need to know that one, and then that related problem also we need to know. And again you need to know pK equals to minus of log Ka base 10. Same way pKb will be equals to minus of log Kb into base 10. That related problem also you have to you have to solve. Then pKw also will be equals to minus of log Kw base 10. Yes or no? This basic part you always have to be remember with you, and with this related problem also. Now you look at another very important point, like a buffer solutions. Buffer solution and salt hydrolysis. Buffer solutions you have to revise like this: buffer capacity you have to go with that one. And what are the things, how buffer used to form, how buffer forming, like weak acid and its salt, weak base and its salt. Salt is a combination of weak acid and weak base, as well as weak acid and its conjugate base, weak base and its conjugate acid. Like that you have to go with that one. Buffer capacity, how to define, and then buffer actions, and always you have to remember that acidic buffer or basic buffer. For acidic buffer, pH will be equals to pKa plus log of concentrations of salt by concentration of acid. But always remember, this concentration of salt means concentration of anion. Always remember, otherwise you can get a mistake on certain problem. So that's why concentration of salt means concentration of anion. Same way pH will be equals to pKb plus log of concentrations of salt by concentrations of base. Here salt means concentrations of cation. That part you have to be remember, because whenever cation anion combination is there 1:1, no problem, but cation anion combination is there 2:3, 3:4, then there will be a problem. So that's why better to remember concentrations of anion. So that is important. Like if I say sodium acetate and acetic acid forming a buffer solution, then here concentration of salt means not about the sodium acetate, concentrations of CH3CO minus. That is important. Whenever 1:1 combination, that means sodium acetate and cation 1:1. But if I take barium acetate, so that's why this part will be different. That's why you need to remember this very important idea. And then after that, specifically, if you look at this equilibrium problem, especially ionic equilibrium, it's a database problem. Data change, formula change, problem change. In same mixture, suppose they are giving NaOH mixing with acetic acid. In one case, we will apply buffer solution. In another case, full acid and base completely combine or completely react, and they are forming the sodium acetate. That means the salt is a combination of weak acid and strong base. Then I will apply the salt hydrolysis based on the data. So that's why next part is very important, salt hydrolysis. In salt hydrolysis, you need to know what are the weaker part is there. It may be cation, it may be anion, that will undergo hydrolysis. Strong part will never undergo hydrolysis. Then salt hydrolysis, that things we need to remember. That means for anionic hydrolysis possible. For anionic hydrolysis means, example, if I take CH3CO Na, this salt is a combination of weak acid and strong base. So this is undergo strong, weak part will undergo hydrolysis. That's why anionic part is the weaker part. So this it is an anionic hydrolysis. This anionic hydrolysis, always you have to remember here that formula is there. Which formula we used to apply? This type of salt, pH will be equals to 7 plus half of pK plus pK plus log C. C is the concentration of salt. Salt means concentrations of anion. That way we can calculate. But this formula is typically based on approximation. That's why I used to say that you will not go with that one. First you have to remember like this way. K into KH into Ka by Kw will be equals to 1 for this type of salt. From there Kw, you know, K they will provide, you will get the KH. Again the KH expressions will come. KH expression same way. So KH expressions what it will come, that means H is a degree of hydrolysis, then H will be equals to under root of KH by C. From these expressions if you look at, you will get the C means concentration of the salt, you know, and then KH I am getting from this equation, and you will get the H value. And when you will get the H value, then anionic hydrolysis means this part will react with a water, large amount of water, and it is forming acetic acid plus which is making phi, that OH minus is making phi. So that means immediately here if it is C minus CH, CH and CH, that means once you H calculated, CH will give rise to your OH concentration. From there directly I can get a pOH by applying minus log of OH concentration. Always you will take OH concentration in the form of X into 10 power of minus Y, and directly you can write down pOH will be equals to Y minus log X. Once you get the pOH, then pH plus pOH always will be equals to 14. 14 minus pOH equals to your pH you can get. Then same, that's why I told never apply this formula, because this formula is based on the approximation. That means that approximation 1 minus H will be equals to 1, but that is not always true. If it is not following that things, H is less or equals to 0.1 degree of hydrolysis, then it is okay. But if it is not, then you have to solve the quadratic and you have to get the exact H value. So that's why from this equation you will calculate the KH, and once you get the KH, then you will check the H by putting this equation. If it is matching, fine, otherwise solve the quadratic, get the exact H, and then OH concentration is CH, and then pOH calculate, then 14 minus pOH equals to pH. That way you can go. And then for cationic hydrolysis pH will be equals to, you have to do 7 minus half of pKb plus log Z. That this formula is based on approximation. That means cationic hydrolysis means you will, that way you can calculate, but that this H value always you need to check, otherwise there will be a problem. And the salt is a combination of weak acid and weak base. That means both cationic and anionic hydrolysis pH will be equals to immediately 7 plus half of pK minus pKb. This way also directly KKb they will provided, you can get these things, you can calculate that thing. This is salt hydrolysis related things, you will revise that way. Next part if you look at, there is a solubility. Then solubility always you need to remember how to find out the solubility. That like suppose I have a AXBY type salt is there. X is a number of moles of A into the salt, Y is a number of moles. If the solubility is S mole per liter, solubility of this salt, then immediately what you will get, X amount of these X amount of these things, and this will give rise to Y plus Y amount of A, and this is nothing but a X minus. So you will get like this. That means whatever amount this, like A2B3, so that means 2A, A plus 3, and like this if you look at understood, suppose I have A2B3, then how I will get 2A plus 3 plus 3B 2 minus. Overall charge you look at matching. So that way, that is why I am showing you like this. If the solubility S mole per liter, then here you will get XS and YS. Then KSP expressions will be equals to like this, your to the power X and this things is B will be there, and B to the power Y, B X minus to the power Y. Now A is nothing but how much is there, you look at, A is their concentration XS, so XS to the power x, then b is nothing but a ys to the power y. So then immediately what we are getting? X to the power x, y to the power y, s to the power x plus y. So then immediately you will get what will be the KSP expressions. That KSP expression is nothing but a, if I take this x equals to 2 and x equals to, if I take 2 and y equals to, if I take 3, then immediately you will get 2 to the power 2, 3 to the power 3 into s to the power 2 plus 3. So then 2 to the power 2 means 4 and 3 to the power 3 means 27. 27 into 4, 108 s to the power 5. So that is the general expressions. You can go with a common part also like this. Suppose if you have like this way, that a2b3 will be like this, 2a plus 3 plus 3a 3b 2 minus. If the solubility is s, then it will be 2s 3s. Then KSP expression 2s to the power 2, 3s to the power 3. Ultimately is coming, you look at 2 square into 3 to the power 3, s to the power 5. Same thing is coming. So that is a general way, this is a specific way. But ultimately different types of salt, you have to know how to find out the KSP expressions, that related problem. The first editions JEE 2025, they asked that problem. And then KSP for the salt in reacting cation or reacting anionic part of that insoluble salt, that they are asking. And in presence of common ion, how to solve that type of problem they are asking. So these are the different things you have to revise for the quick revisions, and then only you will be competent to solve the different types of model problems and things. I hope you got the idea how to revise, quick revise the things, particular chapter as far as chemistry is concerned. Is it clear? Okay. Thank you very much. And if you want to get more and more like this type of video and guidance, please come and comment in my video so that I can give you specific support to each and everybody, and everybody can be benefited for upcoming JEE and NEET. Thank you, my dear student. Thank you all.